Welcome. Let's take a look at error as it occurs when we measure quantities and perform calculation based on those measurements. So the amount of error we'll want to first discuss is what's known as propagated error. So it is a fact that whenever we perform a measurement, it is prone to error. The error can be a result of the tool that was used for the measuring, or it can be a result of the person's process in performing that measurement. For example, the computed area value of the area of a circle is only as accurate as the measurement of its radius. If an error in that measurement An error in the measurement of the radius will lead to an error in the computed value of the area of the circle. So let's consider a function with an input that is a measured quantity. And suppose that that measured quantity is A, the radius of a circle in the example we just mentioned. But the measured value is A plus dx, where the dx is some type of measurement error. This error then propagates to the calculated value for f of x. So the error in the measurement of radius will then propagate to the calculation of the area of a circle. And rather than calculating f of x, we calculate the area of the circle with that small error in the measurement of the radius. Well, this results in an error in the outputs, and we refer to that error in the outputs as propagated error. Now, unfortunately, all measurements are prone to some degree of error, and we won't always know the exact value of the measured quantity. So our propagated error, while we've defined it, we cannot calculate it exactly. However, if we have an estimate of the accuracy of a measurement dx, we can estimate that propagated error using differentials. That is, the propagated error due to a small error in measurement is equal to the differential dy equals f prime of a dA. Now, unfortunately, at times we don't know the exact value of a, but we do know the measured value of a plus dx. So this can allow us to estimate the propagated error with the differential. Propagated error is approximately equal to the differential dy, which is approximately equal to f prime of a plus dx, where a plus dx is the measured attribute rather than the true measurement of the attribute. So in the case of our circle, a plus dx would be the measured radius, where a would be the true radius. Note that the measurement error dx, also referred to as delta x, and the propagated error delta y are referred to as absolute errors. They are errors in quantity and they have units attached to them. Now, for any absolute error, delta q, for a particular quantity, we can find its relative error. So, for example, we could consider the propagated error in area to the true area, and that would be relative error. We could consider the absolute error in radius and compare that to the true radius, and again, have relative error. Now we can take this relative error and report it as a percentage error by simply taking that relative error and expressing it as a percentage. So let's take a look at an example to understand these various types of error. So let's take a look at an example. Let y equal x cubed minus 3x. If dx, or delta x, is equal to 0.05, so think of this as the error in your measurement, we want to find the propagated error, the actual change, and dy, the estimated change, at x equals 2. We will also take a look at the percent error and the relative error. Okay, so first let's go ahead and find the actual change. So as we do this, we want to think of x equals 2 as the true value of x. And then because we had this measurement error, so dx we want to think of as our measurement error, then we measured, rather than 2, we measured 2.05. So what we're going to do is we're going to say that the true change in the y value is equal to y at the measured value, so the 2 plus the error in the measurement, so 2 plus 0.05, minus y at the true value. So inserting that into our function, we get 2.05 cubed minus 3 times 2.05. That's our y at 2 plus 0.05 minus y at 2. And our y at 2 is 2 cubed minus 3 times 2. Well, running this through the calculator, y at 2.05 is 2.465125 minus, and our y at 2 is simply 2. Which gives us a difference of 0.465125. So there's our propagated error, or the error due to the actual change in the y values, the error due to true error due to this measurement. The true error in our calculations of y due to the error in the measurement. Okay, so then dy is equal to f prime at our true value is 2, times dx. And so we need to know what f prime of 2 is. So first of all, f prime of x is equal to, and we need the derivative of x cubed minus 3x. So that would be 3x squared minus 3. And now we need to evaluate that at 2, our true value of this measurement. And we get 3 times 2 squared minus 3, which is 12 minus 3, or 9. So dy equals 9 times our dx, and our dx is 0.05. So our dy is equal to 0.45. So comparing these two values, notice that they do agree in the first decimal place, 4/10, and they're somewhat close in the second decimal place, the true value having 6/100, while the estimated value being 5/100 in the second decimal place. So those are our two. Propagated error is the dy, and the estimated change is 0.45, which doesn't look too terribly bad, of an approximation. However, let's take a look at the relative change. So relative change, or relative error in the value of y. So the relative error in the value of y is the change in y over the true value of y. Well, we just saw that the change in y was 0.465125. Now that's going to be divided by the true value of y. Now notice we did compute that as part of our delta y here. We know that the true value of y should be 2. So notice that we have an error of almost 1/2 or 5/10 compared to a true value of 2. So if we calculate that ratio, we find that our relative error is 0.2325 and there's some more decimal places, but that's sufficient. So that's our relative error. And then our percentage error, if we turn that into a percentage, we see that our percentage error is approximately 23%. Well, 23% seems like a rather big error to me. So while the magnitude of the errors didn't look very large, if we put it in context compared to the true value of what it should be, we can see that we have a pretty significant error in letting this input value or a true value vary by something that looks rather small. 0.05 of a variation in the x value produces a 23% error in the output. I hope you find this helpful.